Okay, so this is part two of lab number four, and this is the relaxation oscillator circuit. And recall that we were required to build two relaxation oscillators, one that will cause an LED or a pair of LEDs to blink on and off at a fairly slow rate. And then the other requirement is to build an audio oscillator that's generating an audible tune that we can hear. Um, this is the circuit that we'll be using. This is the basic relaxation oscillator circuit, and we'll use the same circuit for both oscillators that we have to build. You'll find the theory of operation and the math behind it in the last part of the textbook chapter on RC circuits. But briefly, the idea is that you build an op-amp circuit and you deliberately have positive feedback. You see that we have this pair of resistors here. The actual value of these resistors don't matter. You can use 1K, you can use 10K. What matters is that they're the same value. And you have the result that because they're the same value, the output voltage here gets divided by 2, and that gets presented to the plus terminal. And then what happens is, because you have a positive feedback, the output is going to actually be sort of slamming back and forth between the voltage rails, the positive and negative rails. And the consequence of that is that we have a capacitor that's charging and discharging, and it just continuously charges and discharges. And the result is that the output of the circuit is this square wave or a train of pulses. It's going to hit the positive rail, the negative rail, positive rail, negative rail, positive rail, negative rail, and it'll just keep on going as long as we have power going to the circuit. Now, let's talk about voltages and let's talk about timing. Since you have an output that's swinging between positive and negative values, then clearly when you power this circuit up, you need to give it a bipolar voltage supply. And so you have a 6-volt battery in your kit, and what you're going to be doing is basically hacking that 6-volt power supply to give you both 3 and negative 3 volts. So when we build these circuits, we'll use VCC as 3 volts, and then minus VEE, that'll be minus 3 volts. So that the voltage rails are 3 and negative 3, and then the output will be slamming back and forth between 3 and negative 3. Okay, now a very practical matter that we're going to have to contend with for the second half of this is that the output voltage will not actually be 3 and negative 3. It'll be something less than that. And how much less depends on the actual amplifier that you've got. And you're going to find that the output voltage is somewhere between 1 and 1.5 volts less than the power supply voltage. That's just the internal voltage drop within the op-amp. So what we're going to find is that the actual output voltage, instead of being 3 and negative 3, is going to be something like 1.5 and minus 1.5. And that won't have a problem when we're using the audio oscillator, but 1.5 volts is not enough to turn on an LED. So that's something that we're going to have to spend some time on. Now, about timing, the time it takes for this thing to charge up is approximately RC seconds. And so the specific timing, the duration of that positive output pulse is 1.1 RC seconds. And I refer you to the chapter of the text on RC circuits to see that math. So 1.1 RC is approximately equal to RC. And so we'll just go with that approximation here. So that the time that this is on hitting the positive rail is RC seconds, and then RC seconds down here, RC seconds. So this waveform, this device will just continue to throw out a positive pulse of duration, RC, and then a negative pulse, RC, positive pulse, RC, and so forth. Now, what's the frequency of that waveform? Well, the period here is going to be twice RC. So that's RC, so the period is 2 times RC. So the frequency is 1 over that period, 1 over 2 RC. And that's the point we have down here. So the oscillating frequency is 1 over 2 RC. Okay, let's go ahead and take a look at the specific circuits that we're going to be building. So first we have the audio oscillator. And I've just drawn that same circuit here. That's the same thing we just looked at. But I've actually labeled the pins that we're using on the op-amp. Now, the op-amps that we have in our kits, the LM358, actually have 2 op amps inside each chip. So if you want to, you could build this entire lab on one op amp chip. But if you do that, the circuit gets pretty dense and it's hard to actually make the kinds of adjustments that I'm going to show you how to make when we tune up the frequency. So the way I'm going to build this is I'm going to build the audio oscillator with one chip on one circuit board, and then I'll build the blinking LED with a separate chip on a separate breadboard. That way we're sort of keeping things kind of as clean and neat as we can. And so this is the pinout of the op amp chip that we'll be using for both oscillators. We have VCC is +3, and then instead of ground, you've grounded this in previous experiments and labs. We'll be connecting that to -3 volts. So that powers up the chip. And then we have our inputs on pins 2 and 3 and our output on pin 1. And so I've just shown over here, we have the output on pin 1 and we have the inputs on pins 2 and 3, and then the power supply are on 8 and 4. Okay. I'm showing here a variable resistor. I'll say more about that in just a bit. And we have our output is connected to our piezo buzzer. That's a tiny little speaker. Okay, let's just focus in on the lower right part of this. This is where we look at the requirement and the design, and we'll use this information to choose which value of capacitor and resistor we need for the circuit. So the requirement here is that the audio frequency that's going to be played into this is a little audio speaker that we're going to use. The frequency of the square wave that gets played into that is going to be between 200 hertz and 2 kilohertz. So that's the requirement. And so we know that 1/2 RC, that's the frequency, has to be less than 2 kilohertz but greater than 200 hertz. Okay, and so if we just do some algebra here, what we find is that the resistor that we have to use is less than 1/400 C, where C is the capacitor we use, and it's greater than 1/4000 C. Now we have to choose both R and C. You only have 2 different capacitors that you can choose from here. You have a 10 microfarad capacitor in your kit. That's 10 to the -5 farads. And you also have a 0.1 microfarad capacitor in the kit. That's 10 to the -7 farad. So if we start out by assuming we're going to use the big one, 10 to the -5, and you plug that value in here for capacitance, what you'll find is that you need a resistance between 25 ohms and 250 ohms. Now that's a pretty small resistor. And we want to avoid using really small resistors and really big resistors. And so rather than get down to a small value of 25 ohms, what I want to do is show you what happens if instead of using the big capacitor, we use the small one, 0.01 microfarad. And if you plug that in here, you'll find that you need a resistor between 2.5 kiloohms and 25 kiloohms. And so now, fortunately, in the kits, you have 2 of these. You have a total of 3 variable resistors. And in the previous part of this lab, in 4.1, we looked at the 1 megohm variable resistor that was labeled 105. You also have 2 100 kiloohm variable resistors that are labeled 104. And so what we're going to do is we're going to use this. This is a variable resistor, and you can adjust the resistance between these 2 terminals anywhere between 0 and 100K. And so you can see that this range of resistance values is nicely going to be covered by the lower end of this. So the R and C that we're going to be using for this, the capacitor is going to be our 0.1 microfarad, and then for our variable resistor, we'll be using that 104 resistor. And so that's why I've shown the resistor as having a diagonal line through it, which indicates it's a variable resistor. Okay, I'm going to start to build this, but before I do, let me just show you kind of how I'm set up to do this. I have one circuit board that's going to be for the audio oscillator, and then here's my pile of parts that I've gathered up for that. And I've just taken and looked at the circuit and gathered up all the parts I need. I also, just so you'll see, I have another circuit board with an op amp on it, and I also have a pile of parts I need for that. And this is going to be for the blinking LED circuit, which we'll look at next. And I just wanted to show you that I kind of have all of this stuff set aside. So I'm going to move all this over here, and we're going to start to work on this audio oscillator circuit. Okay. Now, let me just say a little bit about the power supply. We said that we need +3 and -3 volts to power up this circuit. Where are we going to get plus and -3? Well, we have our battery packs here, and they have two wires on them. And we know that the red wire is 6 volts above the black wire, or the black wire is 6 volts below the red wire. If you had two of these, then we could power up this circuit with plus or -6. But what we're going to do instead is, if you take a look at that power supply, it's four 1.5 volt batteries that are all wired in series so that you have 6 volts between the ends. What you need to do is find the point and you can do this by just observing the battery pack, or you can use a multimeter. You want to find this middle node on here, and you want to just shove a wire in there, like I've done here. I've just taken one of our little wires and I shoved it into there, with the result that, and I'm going to use that wire as our ground. So if this is our ground, then I have 3 volts above that and 3 volts below that. So our red wire is going to be 3 volts. Our ground is going to be white. And then our black wire is going to be our -3 volts. And that's what I've done with this power pack here. And then when we actually hook it up onto the circuit board, the way I'm going to do that is I'm going to have the positive rail being this top row, as we always do. But I'm going to use it, so that'll be 3 volts. And then the rail just beneath that, I'm going to use that for -3 volts. So I'll have 3 volts and then -3 volts. And then I'm going to have ground, which is our white wire down here. So that means we have 3 power supply terminals that we're keeping track of: ground, +3, and -3. Okay, so we're going to start building this. And I'm going to start out just by powering up the op-amp circuit. And so the op-amp circuit requires 3 volts into that positive rail. That's pin 8 to the positive rail. And then we need our -3 volts, which is pin 4, and that's going to go to that negative rail. Okay, so that powers that up. Okay, now I'm going to just work on these two 1K resistors. So you'll see that between pin 1 and pin 3, I have a 1K resistor. So I'm just going to take and kind of tuck that right into there, between pin 1 and pin 3. That's this resistor right here, pins 1 to pin 3. And then from pin 3 to ground, I have another 1K resistor. So pin 1, 2, 3, I have this resistor, and then that's going to go to our ground. Okay, and it's worth reiterating, this down here, this rail is going to be our ground rail. That's the white wire from the battery. Okay, up top we have our 3 and our -3 volt rails. So we've just built this part. Now I need to connect the capacitor and the variable resistor. The capacitor goes between pin 2 and ground. So that's this little capacitor here. And that just goes between pin 2 and ground. So pin 1, pin 2, and ground. So it's a little bit crowded in there, but as long as you're careful and you double check that you've got things in the right pins, you'll be okay. Okay, now I have to fit 2 more things on this board that can be a little tricky. There's the piezo speaker. And so this is a little tiny speaker. It's like the speaker that you have in your cell phone. It's a little piece of piezoelectric crystal. And when you apply a voltage across it, that voltage is going to create a strain in the crystal. And it's going to actually cause the crystal to, a positive voltage across it will cause it to bend in one direction, and a negative voltage will cause it to bend in a different direction. And so when you have an oscillating voltage, high, low, high, low, high, low, or positive, negative, it's going to cause the crystal to sort of oscillate back and forth, and that's going to create a little sound wave. Now, the thing about it, it has tiny little leads on it. So when we put it in here, we just have to remember which leads we're putting it in. So I'm putting it in, and it's going to be on column 26. Right, I pushed it in there, and I had to keep note it's in column 26. And we're going to connect that piezo speaker between pin 1 and ground. So pin 1 to pin 26, and then from pin 26 to ground. Okay, now we have to connect our variable resistor. And we wanted that resistor to be between 25 kiloohms and 2.5 kiloohms. So I'm going to start out by pre-setting the resistor to 25K. I'm going to get my multimeter, set it up on resistance, and I'll use the middle and the terminal that's farthest away from the adjustment screw. So I'm going to use these two, and I just want to set those up for 25K. Okay, and you can see it's pretty close. It's because I've already been fooling around with this circuit before cutting this video. You know, it would have started at 100K. So if you take one out of your kit, it's going to be sitting there at 100K, and then you can just adjust it down. And we'll bring it down to 25K. And we'll adjust it once we've got it in the circuit. So this is the biggest value of the resistor that we'll be using. And this should correspond to since it's the biggest resistor, it's the biggest value tau time constant of the circuit, meaning it's the longest duration pulse or the lowest frequency. So this should correspond to our 200 hertz output, our lowest frequency output. Okay, so I'm going to pop this into the circuit board, and I also have to keep an eye on where I'm plugging it in, because once you put it in, you can no longer see the little leads. So I'm going to be putting it in with the wires that we need are going to be on columns 7 and 10. 7 and 10. Now this resistor goes between pins 1 and pin 2 of our op amp, and then it's going to columns 7 and 10 here. So pin 1. It's going to go to 10, and it doesn't matter which goes where. It's just a resistor. You can turn it around, and it's not polarized. Okay, we said pin 1 and pin 2 are going to go between 7 and 10. Okay, if we've done everything correctly, then when I apply my power supply, this circuit should start singing at 200 hertz. Oh, it looks like I've got a break in my wire there. That's sort of unfortunate. So I'm going to have to replace this wire. So I'll have to pull that one out since the lead is broken. Shove another one in there. Okay, and I wanted to avoid using white and black because, you know, that would just confuse us. I want to use a wire that's kind of neutral in color for ground. Okay, there it is, and you can hear it. So that's our 200 hertz. Now, you don't have tools that you can use to actually measure the frequency. You don't have things like tuning forks necessarily. You don't have an oscilloscope. So the actual precise value of the frequency doesn't matter. But I just want to show you that when I use my potentiometer trimmer to change the resistance, you'll change the pitch. So just listen. So it's going lower in frequency. Higher. Okay, so you get the idea. So by changing that resistance, we can change the frequency of that tone. So this completes the audio oscillator part of this lab. Now, we're going to come back to this because when we're finished, we want to have both the audio oscillator and the blinking LED. So what I'm going to do is I'm going to disconnect the battery. You want to be careful always that these wires don't connect to each other in short, because that'll kill your battery. So I'm going to take this circuit and put it aside. And now we're going to look at our LED blinking circuit. And that's here. So the circuit is just the same as the previous circuit that we looked at. It's all the same wiring. You see we have an RC circuit that's connected in the same way using the same pins, and we're going to use a different op amp on a different board. But let me just say a little bit about sort of the requirements and the design, so we can choose appropriate values for R and C. So in this case, the requirement was an LED that has an oscillator that has two LEDs. We're going to use a green one and a red one. And we want them to each be on for half a second. Half a second green, half a second red, half a second green, half a second red. So that in other words, this whole thing is blinking at 1 over half a second, 1 over twice half a second, or 2 hertz. This is what the output waveform is going to look like. And now we're powering up the op amp with 3 and -3. And it turns out, and I'll show you how to measure this, that when this is oscillating, it gives me a positive voltage of 1.5 volts and a negative voltage of -2.2. So instead of being 3 and -3, it's 1.5 and -2.2. And that has implications on how we set up the output circuit. Before we get into that, let's just look at how to choose R and C. We want the duration of each of these pulses to be, which is RC, seconds long, right? We want each of those to be half a second. So we want RC to be 1/2 second, or R is 1 over twice the capacitance. We have 2 capacitors, a small one and a big one in our kits. If we use the small one, 0.1 microfarad, then we'd need to use an enormous value of resistor, 5 megohms. First of all, we don't have one that big in our kit. Second of all, when you get to such a large value of resistance, then other things in the world, like your body, actually has resistance significantly less than that. And if you touch it, then you can change the circuit considerably. So we want to stay away from such a very large value of resistance. If we use a capacitor, the big capacitor, 10 microfarad, then we'd need R equal 50 kiloohm. And 50 kiloohm is nice because, we have these 104 variable resistors, which will range between 0 and 100K. So our sort of design choice here is to use the 10 microfarad capacitor and the 50K variable resistor. Okay, so I'm going to go and start to build that. And what we're going to find, well, I'll just go ahead and build it, and then you'll sort of see what the issue is. We're going to take the output and we're going to connect that through resistors to an LED, another resistor, and an LED. And the idea is let's say we want the green one to be glowing when the output is positive, and we want the red one to glow when the output is negative. So the way we'll hook that up is when this is positive, we want the green one to glow. So we're connecting the anode to our output through a resistor. And when the red one, we're going to reverse the polarity of that. So it's the cathode that's connected to the output, so that when this output is low, then we have the cathode going to the lower voltage. We're grounding the anode, and the red LED should glow. So let's go ahead and start building this circuit. I've already got the chip in there. Okay, the first thing we're going to do is power up the chip. And as before, we're going to use a 3-volt rail and a -3-volt rail. So I'm going to connect this to -3 volts. And then down here, we'll have our ground rail. Okay, as before, we had our 2 resistors, and I had said the value of those doesn't matter as long as they're the same. And so one goes between pin 1 and pin 3. So we'll just take and tuck that in there between pins 1 and 3. And then we have another 1K resistor, and the 1K resistor has colors brown, black, and red, which you can also measure it with your multimeter. Okay, that second resistor is going to go between pin 3 and ground. So from pin 3 to our ground rail. All right. Okay, now we have to have our capacitor and resistor. The capacitor goes between pin 2 and ground. And this is one of these electrolytic capacitors, so it is polarized. It has a minus on it pointing us to the negative polarity, which is the part that goes to ground. So this is going to go between pin 2 and ground, and we just tuck that in there. Okay, now we also have to put in our variable resistor, and that's going to go between pins 1 and pin 2. And so now we have to decide where we want to put this. And this is a question we have to do a little bit of planning. We know we have to have a couple of LEDs. That's the output side of this board. And we also know that we have to put this variable resistor somewhere in such a way that we can get our pot trimmer in there to adjust the blink frequency. So we have to sort of think a little bit about where we want to put it. I'm going to put the variable resistor on this side so I can adjust it as I need to, and then I'll put the LEDs over on this side. So the variable resistor goes between pins 1 and 2. So I'm going to push it in here, and I'm going to put it in, and I'm going to note that it's going to be in columns 6 and 9. And we want to connect those to pins 1 and 2. So pin 1 goes to pin 9. Pin 2 goes to pin 6. Okay, so this way we have plenty of room to get at that if we need to adjust the frequency. Okay, now we're going to work on the output. So from pin 1, we're going to have 2 LEDs. It's getting a little crowded in here. I'm going to just connect that right here. That's going to go to 2 LEDs. The LEDs each have a current limiting resistor. So let's first address, I'll get the green LED, current limiting resistor. And notice that I'm showing the green LED going to -3 volts. You know, you're accustomed to connecting one of this through a resistor, the LED, and then to ground. So first I'm going to connect it to ground, and then I'll come back and show you why I've connected it on the drawing to -3. The long wire, the anode, goes at the other end of the resistor, and then I'll put that into ground. Okay, and now we have our red LED. Everything the same except that we're turning it around. We have the anode going to ground. And we're connecting that back to this output node, which we've made available with that yellow wire. Okay, so now I'm going to power this circuit up. And what we're hoping to see is that the red and the green LEDs will alternately blink. Okay, and you can see that the red LED is blinking, but the green one isn't. It's actually blinking pretty slow, so we have to adjust the frequency of it, but notice that the green one isn't blinking. And the reason is, I'm gonna show you what's going on here by measuring the output voltage here. This is the output from the op amp that's turning on those LEDs. I'm going to measure that with my meter. So I'm going to connect this probe, that's to the black wire of the meter, and then I'm going to measure Okay, and so notice that the output voltage goes from, it's going fast, but we'll have to sort of catch the peak. 1.56 minus 2.2. 1.56 minus 2.2. 1.57 minus 2.2. It's going high and low, high and low, high and low. Okay, I'm going to take the meter away. So what's happening here in the circuit is that the output voltage is swinging between 1.5, or it's actually 1.57, and 2.2. And when it's high, that's when we're trying to drive the green LED. Right now it's configured 1.5 volts through a resistor, green LED, and then to ground. But we know that the turn-on voltage of that LED is 2 volts. So this is not a large enough voltage to turn that on. On this side, when this goes negative, it's minus 2.2. That is enough voltage to turn on this LED, because when this, we've got the anode grounded, and when we bring this down to minus 2.2 volts, we do have forward bias on that LED. But what's happening is, given the relatively small voltages that we have on our rails, given the practical voltage drop between those rails and the output, we're really only getting 1.5 volts when the op-amp output goes high. That's not enough to turn on the LED. So what we're going to do is, instead of connecting that cathode to ground, I'm going to connect it to minus 3 volts. So that way, when this output is high, it's going to be, we'll have 1.5 volts here, minus 3 here, and that'll be sufficient to turn on the green LED. So I'm going to take that one, and I'm going to connect it to my minus 3 volt rail. Okay, and now you can see I've got them blinking in alternate. Okay, it's a little slower frequency than we wanted. The requirement was that they're only on for half a hertz each, and you can see these ones are on for on. They're on for a longer period of time. So I'm going to adjust this resistor to get them to blink faster. And I don't know which direction to turn it, so I'm just going to try turning it in a certain direction and see if I can get it to blink faster. I think I'm going in the wrong direction. You have to be patient in tuning these potentiometers, because I find it keeps slipping off. Okay, you can see I'm starting to get it to go faster. Blink, 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 blink. And I can make it go even faster if we want. We could actually get to the point where, I've got this resistance so small that those things, they'll appear to our eyes. Let's see if I can take it down there. Maybe I can take it down to the point where, so now we can't even see them blinking. What happens is they get to be blinking so fast that to our eyes, they look like they're on all the time. They're just dim, because our eyes can't actually see that flicker. So they're blinking back and forth, but it's too fast for us to discern. Okay, so this is about where we want to be. Get to about half a hertz. Okay, so now I want to bring both of our boards together. And the way I'm going to do that is I've got my battery pack here. This one's all powered up, and I'm just going to connect the voltage rails and the ground between these. So I need to connect my 3-volt rail. I need to connect my -3-volt rail, and then I need to connect my ground rail. And when I do that, we should have blinking and singing at the same time. And you could adjust each of these if you wanted to adjust the pitch, the tone here, or the blink right here. Okay, so that's it for that lab on relaxation oscillators.